Hello and welcome to another session, rather the last part of the splitting of d orbitals, that is Tanabee sugano diagrams for D2 system under an octahedral environment. I am your instructor, Saurabh Maktibodh. Let's just try to understand what we did in the previous videos. In the first video of this kind, we have been talking about the splitting of d orbitals under an octahedral environment and stating that it splits into Eg and T2g orbitals. In the second video, we have assigned the term symbol for a D2 ion in an octahedral environment. Why we took this as a case study? The only reason is we are now willing to incorporate the inter-electronic repulsions that are likely to take place when we talk about the correlation diagram, construction diagram, and so on. Configuration of D2 ion under weak interactions, that was the matter of investigation for the next video, that is the 7.03 video, in which we have assigned the terms and various terms were splitted under the weak interactions for an octahedral environment and then in general for various systems. Configuration of D2 ion in a large splitting. Yes, that was the 7.04, the point of discussion for our entire theme, and actually we are heading towards the construction of the correlation diagram for a D2 system, and that is our main and the major focus of the entire studies. So, shall we begin? Yes, proceed. In the earlier videos, we have studied that, and now we are trying to establish the fact that the construction of correlation diagram is based on two major principles. First one, in going from weak to strong interactions with the field, the symmetry properties and their spin multiplicities are preserved. That means the same symmetry with the same spin multiplicity are to be joined. And number two, in going from weak to strong interactions with the field, states of the same spin multiplicity and symmetry do not cross each other. This is known as non-crossing rule, and this rule is actually very useful in deciding if we have states of the same symmetry and same multiplicities. Then we would do this correlation in such a manner that the two lines do not cross, and this is known as the non-crossing rule. Now it will be clear in the coming session. This is how correlation diagram looks like. In the earlier videos, we have studied that we have a free ion for a D2 system. Various terms were assigned in terms of their increasing order of energy. You have 3F, you have 1D, you have 3P, 1G, 1S, and so on. And under the weak interaction or the loose interactions, we have seen that they are splitted into various symmetry terms, various symmetry symbols, various irreducible representations. And what is important is we have seen that the multiplicity is the same as that of the parent term. For example, here it is 3F, here is 3A2G, 3T2G, so 3T1G. All of them are having the same multiplicity, that is 3. Similarly, when a d orbital is examined under octahedral splitting, we have seen that it splits into Eg and T2G levels in terms of symmetry properties, and therefore because they are 1D, their multiplicities are 1. Similarly, P, a triple degenerate, splits into 3T1G and 1G, that goes into 1 Eg, 1T1G, 1T2G, 1A1G, and 1 as being spherically symmetric. There is no question, it belongs to only A1G category with the spin multiplicity of 1 only. On the extreme right of this representation, we have assumed that, and that has been elaborated in earlier videos, that what would be the extreme case? We have T2G orbital containing 2 electrons, or 1 electron is present in T2G and 1 electron is present in E1G or Eg1, and there is possibility that both the electrons are there in the excited state, that is Eg2 kind of species are also possible. Now this is extreme in terms of energy. So T2G, 2 electrons in the ground state, that is dx square minus y square and dz square, both of them having the same electrons and 1 electron each, or either 1 electron in excited state, 1 electron in ground state, or both electron in excited states. So that is the order of the energy that has been displayed here. By some means, it has been also shown by very lucid way, or rather, by simple connection with the terms and spins, we have been able to find that the T2G is equivalent to 1A1G, 1EG, 1T2G, 3T1G, and so on. And similarly, T2G1, EG1, they have 1T1G, 1T2G, 3T1G, 3T2G, and for this 1A1G, 1EG, and 3A2G. Fine. Now, nextly, what happens is we are left to correlate the things. And how to correlate? If you start from the 3F term to ground state term to the extreme right, we are left with the option to join 3T1G with the 3T1G by saying that the same symmetry and same multiplicities are preserved, because if you notice that here is 3T1G and 3T1G is also here. Now, if you join this, there is another option that 3T1G from this point may connect with the 3T1G from this. But if we are going to join these two terms, what is going to happen is we are violating the non-crossing rule, and therefore what should existed? It must be something like that. So 3T1G from 3F should be joined to 3T1G of T2G2 state. When you are talking about the next term, 3T2G can be joined in the manner that has been demonstrated, or this can be done the only way that is being displayed. Very fortunately, if you see on both the sides of the diagram, 3T2G is only once that has appeared from this extreme right, and similarly you have only 3T2G and 3T2G. They are going to get matched. So there is no question about the second term. However, when you talk about similarly 1T2G, there are options that has been displayed here. There are 1T2G is here, 1T2G is here, 1T2G is also here, and 1T2G is also here. And if you join in the manner that has been done right now, again, as you know that we are going to violate the rule, and therefore what should have existed is, just observe that these lines would go in the manner that 1T2G is not crossing with the 1T2G structure. Now we are left with more options. If we talk about 1EG, now 1EG is here in 1G, it is also here in 1T, it is also here in EG, and it is also here in T2G. Now again, I'm just trying to explain that the correct way would not have been this that is displayed. The correct way would have been join in the manner that the non-crossing rule gets protected. The another option is 1A1G from 1G and 1S respectively could have joined with 1A1G of T2G or 1A1G of EG, and if we do it, this is again the violation, and we would therefore recommend this kind of correlation. And then lastly, the option 1T1G has to be joined with 1T1G, and that is the only quantity left on the right and the left hand sides. So this is how a correlation diagram can be constructed. What does it explain? It explains a free ion with its various terms, an ion under very extremely strong interaction. So in under extremely strong interactions, it is going to split into various levels. Here we have, on the other hand, there are the weak interactions based on the spectroscopic terms, and intermediate positions or intermediate interactions have been shown in the middle of the diagram, and therefore it can be used to verify or to understand how this diagram can be used to actually determine the energies of a particular ion under the influence of various ligand fields. So that's it. If you just want to watch it again, just observe it very closely. You have various terms, spectroscopic terms, symmetric terms, and these symmetric terms are now, according to their multiplicities of their parent terms, have been shown as usual here on one side, and similarly this is for weak interaction. And when you talk about an extremely strong interactions, there is possibility that both electrons are in ground state with various terms that we have actually developed in the earlier video. Similarly, we have the possibility of T2G1, EG1, both electrons present in T2G and EG the level itself. And the last situation is both the electrons are there in the extremely unstable higher energy states. And now what is left is to join. And I left this to you. You simply watch this. What are the possible situations? And I suppose my students or my participants, they can simply observe and now try to understand correlation, the method of correlation. There are only two things that has to be taken into account. Number one, same multiplicity, same symmetry. Number two, there is no crossing. If you keep these two facts in your mind, the rest of the things are quite easier. And this is how a complete Tanabee sugano diagram or rather this is a sort of correlation diagram is formed. But that's not the all. The point is, the actual Tanabee-Sugano diagram looks something different from what has been displayed. If you just make a glance of the entire figure, you will see that on one side you have terms and they're symmetric terms, symmetric representations, and on the other side you have extremely strong interactions corresponding to their symmetry properties. But actually, it does not look like this. The Tanabee-Sugano diagram has a somewhat different structure. What is actually done there is we just omit these terms on one side. We only take the terms one side, and then we try to correlate these terms with their varying spectroscopic and symmetric properties. Still, that picture is not the Tanabee-Sugano diagram, because the horizontal line that is actually a ground state energy has an inclination not parallel to the x-axis, and therefore what we would like to do is we would like to move the 3T1G line in such a manner so that it transforms from the below x level to the ground x level, that is something like this. You just look at this, see how the things are getting shifted from one side. You have one side, you have 3T1G, it was lying originally on the downside. Now we have shifted this 3T1G, and accordingly various other lines have also been moved, and this is how a Tanabee-Sugano diagram looks like. So it's pretty easy, and though the people who actually do some work in the ligand field theory, crystal field theory, it has a great importance to these people. Now what you can simply put all the scales as well, and once you do the scales also, then it is quite easier to find out the energy under the various parameters that has been displayed, or depending upon the strength of the ligand and a particular ion in a D2 state. In similar manner, we can construct a correlation and a Tanabee-Sugano diagram for D3, D4 and other states that we are not going to display in this session. Sometimes probably on the demand of the audience, we may display the another Tanabee-Sugano diagrams for various other systems as well. Thanks for watching. Have a great day. Thanks again.